Good afternoon. So today we are going to see about the power flow analysis by using the Newton-Raphson method. As this algorithm is an extension of this Gauss-Seidel method. As I said, the Gauss-Seidel method, you'll have, say, for example, there are three methods we already discussed, like Gauss-Seidel method, Newton-Raphson method, and fast decoupled method. So at last, we'll compare all these three algorithms. What are the advantages in Gauss-Seidel method? What are the advantages in Newton-Raphson method? And what are the advantages in the fast decoupled method? Today, we'll see what are the algorithm steps for the Newton-Raphson method. Once you understand one algorithm, that is Gauss-Seidel method, the steps are all same for all the algorithm. See, for example, you need to calculate the Y-bus matrix, means same we did. Next, flat start means same, flat start. Like that, then calculation of VI's specified value, QI value, next PI calculated value, QI calculated value. The formulas are almost same. Formulas are same as like in the Gauss-Seidel method. The thing is that algorithm steps only vary, and that too here also similar algorithm. Some limits checking also there. Limits checking also there in your Gauss-Seidel method. So here we are computing the Jacobian matrix and is obtaining the state correction vector. That's all. There also the same, the procedure is same. There also we are calculating and here we are checking the limits, reactive power limits violation. Then you after that you are change in the real power, change in the reactive power that we are calculating. That matches. So like that same as in the Gauss-Seidel method. So you note on the steps. Step number 1, get the values for the buses. So first we need to get the values for the buses. That is the impedance or admittance. So whatever the values, you need to take down the values. Next, step number 2, get the values of the impedance bus for the given buses. Values of impedance bus for the given buses. Say for example, what are as I said, what are the impedance values that you need to identify, get the values means, say, for example, if you are programming, you need to get all those values. If you are not programming, you need to identify the values and you need to formulate the Y-bus matrix, same as in the Gauss-Seidel method. Formulation of Y-bus matrix up to the same. Next, step 4 also same. Assume the flat start. Assume the flat start, that is VI initial value 0 is equal to 1 plus J0 or 1 at the angle of J0 degree. For I is equal to M plus 1, M plus 2 up to N. Here also for delta I is equal to 0, for I is equal to 1 to N for all the buses except the slack bus. Next, we need to calculate the VI is equal to VI specified value for all PV buses and slack buses. Specified values that we already did. How to calculate the VI specified value or VI new values that already we did. Next, for load buses calculate PI calculated and QI calculated. PI calculated value, QA calculated value. That also the formula, you know, same formula that as you used in your Gauss-Seidel. Next, step number 6, for PV buses, check for the Q limit violation. That is the reactive power limit violations. If QI minimum is less than QI calculated, less than QI maximum, then the bus acts as if it is within the limits, that is QI calculated value is within the minimum and maximum operating limits, then the bus acts as a PV bus. If QI calculated value is greater than QI maximum, then you need to fix the QI specified value is equal to QI maximum value. If a QI calculated value is less than QI minimum, then you need to set QI specified value is equal to QI minimum value. for PV bus will act as a PQ bus. Next, step number 7, mismatch vector. That is change in the real part. Del Pi is equal to Pi specified value minus Pi calculated value. Similarly, del Qi is equal to Qi specified value minus Qi calculated value. Next, compute del Pi maximum value, that is the maximum of del Pi. Okay, so maximum value of del Pi that you need to calculate for I is equal to 1 up to n except the slack bus. Next, Qi maximum value, that is maximum of del Qi for I is equal to m plus 1 up to n. Next, up to here, it is common with your Gauss-Seidel method. So here what we are doing is, here this limits up to here it is common PA QA value, and we are calculating the change in the voltage value that we are doing. But after this, you need to check whether the reactive power is within the limits or not. If it is not, it is violating the minimum and maximum operating limits. So you need to fix those reactive power to its minimum and maximum operating limits. So that is there in the algorithm like this. Next, after that you need to calculate del PA, del QA. Next, del PA maximum, del QA maximum. Next, you need to compute the Jacobian matrix. Jacobian matrix J is equal to dou Pi divided by dou del into dou Pi divided by dou B. Next, dou Qi divided by dou into delta. Next, dou Qi is equal to dou into B. So this is how you need to calculate the Jacobian matrix. So here obtain the state correction vector. Next, after that, obtain the state correction vector, that is del into del V. Okay, in single vector itself, you are calculating in single matrix itself, we are calculating change in the phase angle and change in the voltage. That is equal to Jacobian inverse of del P divided by del Q. Next is step number 11. Update the state correction vector. State correction vector, that is V nu. That is voltage U is equal to voltage volt plus del V. Next, delta nu. Delta nu is equal to delta volt plus del. Okay. So new voltage is equal to voltage plus change in the voltage. Same as we did it in our Gauss-Seidel method. Next, new delta is equal to old delta. That is old phase angle value plus change in the delta. So del. Okay. Del into dou. So this procedure is continued until del PA is less than this tolerance limit, that is this epsilon. This epsilon value you take as 0.001, and it depends on the problem. If you take 0.01 also, the value it will execute, and it depends on a value it depends on the user defined how fast you need to calculate. Otherwise, the program will run for n times. Next, otherwise, go to the step 3. If this is not within the limits, the epsilon is not within the limits, you need to go to the step 3 and you need to proceed the same. Again, you need to formulate the Y-bus matrix and the same VA specified values, everything we need to calculate for the second iteration. Second iteration, you need to calculate. Again, you need to calculate with the next iteration. K is equal to 0. You take in K is equal to 1. So next iteration, you need to calculate all, and you need to compare what is the change in the voltage, what is the change in the phase angle, whether it is the answer is merely same or not, like that. So this you can easily program. This is the algorithm for the Newton-Raphson method. You can easily program with your MATLAB or otherwise your Python programming also. So this is the logic. So rest all are with the users. So I can't able to comment on your program and all. The thing is that we need to get the final answer. This del and this del V. Okay, change in the phase angle and as well as the change in the voltage we need to get. That's all. So just all programming skills is yours, and how you are taking the input, how you are taking the output, that and all the user define. So this is the algorithm for the Newton-Raphson